Here is a video lecture on light and energy, making this since many students are going to be absent, as well as I think this topic is conceptually demanding enough that it warrants a video lecture so that you can go back and revisit this topic if you need to hear it again. So in the last class, we discussed and introduced the ideas of kinetic energy and potential energy. To refresh, kinetic energy is the energy of motion, and right now we're studying the atom, and so we really care about the subatomic particle of the electron and how it's moving, and that's going to be our focus in terms of the kinetic energy of that. Potential energy is the position of the electrons, and that's going to be relative to the nucleus. So depending on how close or how far away an electron is, its position, its physical location around the nucleus of an atom, is going to determine how much potential energy it has. There are other applications of kinetic and potential energy, but those are what we're going to focus on right now. So here we have, I'm going to begin to discuss about what you saw in the flame test lab, as well as what you will be seeing in terms of how do electrons and energy interact. So electrons are normally found in very specific locations around the nucleus. So these locations, wherever the location where an electron normally resides, is called the ground state. And so that's just a vocabulary word you need to know. However, electrons can absorb energy, and they typically absorb maybe a photon of energy from some light source. Maybe they absorb energy from an electrical source. They absorb a form of kinetic energy, and that will change the position of the electron, as it says here. And so what happens, and I'm going to draw this out, but in words trying to describe it, but when an electron changes the position, once it moves, it absorbs some energy, it's now going to be in what's called the excited state. And when it's further away from the nucleus, it's going to have increased in potential energy. So let me kind of draw this out a little bit so that we can look at this. So this is my little rendition of an atom, and I'm making the nucleus right in the center here, that black dot. And these are trying to represent rings where electrons may lie around the outside of outside the nucleus of an atom. And we're going to call, these are energy levels. So do this one maybe. We're going to make this like the first energy level, this one the second. And these are just positions where electrons can reside around the nucleus. And they're just certain positions. So any electron on any of these energy levels is going to have, if it's normally found here, so if I just draw an electron here, let's just say that electron is in the first energy level. Now we know that electrons do not orbit around the nucleus of an atom in concentric circles, but it's useful to look at it this way when we're trying to describe what's happening when we see light, or how light intersects with electrons. So if this electron that I've drawn here, if this is where it normally resides, it's a ground state position, it could potentially get hit with some kind of energy. So this is my little zap of energy. And remember that energy has to be conserved. So if it absorbs some energy, this electron, it's going to move. Now, what's new here is we're going to learn how is that electron going to change its position. So when an electron absorbs some energy, it's going to be moved further away from the nucleus. So it might move to the second energy level. If it absorbs enough energy, maybe it can go up to the third energy level. And I'm not drawing more energy levels, but if there was the fourth or the fifth, further energy levels, pretend these are rings that go around the whole thing, an electron could potentially move further away. It's just however much energy it absorbs, okay? Now, Now let's just say this electron's up here, okay? And an electron, this would be considered the excited state. Down here, let me just kind of draw this back in. Down here, this would be the ground state, wherever the electron is normally found, okay? Now, the ground state is stable. It's low in potential energy. It's very stable. An excited state is higher in potential energy. But this is unstable. The excited state is unstable. And an electron will not stay here for very long. And so what will happen is it will fall back down to its ground state position, which is stable. Okay, so make sure you label this as a very stable position. It's where the electron's normally found, so you'd expect it to be stable. But if an electron absorbs some energy, okay, so it gets zapped with some energy, it gets hit with some electricity or some light source, some electromagnetic radiation, it's going to move to an excited state. It's going to stay there for less than a nanosecond. I mean, electrons are constantly in motion. But the exciting part is that when it falls back down, so when it makes this move from the excited back to the ground state, so this move right here, when it moves back down, it is now going to be back in lower potential energy. Remember that we just saw this movie that the total energy of a system is the sum of the kinetic energy plus the potential. So the energy has to be conserved. So when that electron decreases in potential energy, it's moving back to the ground state. It is going to release energy when it falls back down in the form of light. Now, what light it is going to be dependent on how far it got promoted and where it's falling back out. So let's just say it fell from 3 to 1, and let's just say that that's green light. It's not, but we're just going to say that it is for this little picture I'm trying to draw here. So we'll say it emitted green light if it doesn't want to stop erasing what I'm doing. Okay, so green light there. Sorry, that's a little messy. So this is, I have other pictures that's going to describe this, but I just want to have this diagram so you can, if you've been following along, hopefully you can follow it. So in words, let's go down here. So what I'm trying to depict in that picture is that when an electron absorbs energy, which is also called a quanta, okay, it's just a packet of energy. So however much energy that went in, okay, however much energy that electron absorbed, it has to be released, okay? And so if it moves to a higher position, if it's higher in potential energy, when it releases the energy, when it goes back down to the ground state, it's emitted as kinetic energy. And light is a form of kinetic energy, okay? And if it gets emitted in the form of light in the visible spectrum of the electromagnetic region where we can see it, then we see the different color lights. And this is what you saw in the flame test lab. So the different colors are literally electrons moving up and down from the ground state to the excited state and back again. So the emitted energy, the packet of energy that we see, is this band of light, all right? And scientists can then measure, and we can calculate, you know, each light, which we've already been doing, the wavelength, frequency, and energy. And every single color of light in the rainbow from Roy G. Biv has its own unique wavelength, frequency, and energy. And that kind of ties back into what we've been studying with these formulas, okay? So every single color of light has these, and beyond the visible spectrum that we can see, like we've talked about, any kind of light, whether that's microwaves or visible light or ultraviolet rays, has its own unique wavelength, frequency, and energy. Here's a maybe cleaner version of what I was trying to draw, a simplified version. It doesn't have everything that I was talking about. But if we look here at step 1, okay, again, this is the nucleus, this blue thing, and you've got an electron. If the atom absorbs energy, okay, not just light, but the added energy causes electrons to jump from a ground state to an excited state. And this one just has it from one energy level to another. So then this electron is now in the excited state, will not stay there. And so it will, I don't really like this word, it doesn't lose energy. It just changes from potential energy to kinetic energy as it falls back down. And as it falls back down, it releases the energy, so it doesn't lose it. It releases the energy it had absorbed in the form of light. So we're able to see that because our eyes detect from 400 nanometers to about 750 nanometers wavelengths. Our eyes allow us to see that. So this is kind of a simplified view, but if that helps you with what I was just depicting. Now, who actually talked about this and kind of is the frontier work? So if you remember Niels Bohr from your video lectures on the scientists, he won a Nobel Prize for his electron cloud model on the hydrogen atom. And he was the first scientist who said that electrons could only exist in specific energy levels or orbits around the nucleus. Now, he wasn't completely right because electrons don't orbit around the nucleus like planets orbit around the sun, but he was right in that there are energy levels, and energy is a quantized factor in terms of electrons being promoted to different regions or outside the nucleus of the atom, and he was a pioneer in this work. So this kind of breaks down what I'm talking about in terms of his planetary model. So if you see this picture over here, okay, the ends represent energy levels. They're also called the principal energy levels. And conceptually, it's important that you know that an electron that is further from the nucleus, so if you have an electron on the first energy level versus the fourth, this electron out here has more energy. Okay, remember that the nucleus has a bunch of positive protons in there. Opposite charges attract. Electrons want to be as close as possible to the nucleus of an atom. They're more stable. However, remember that like charges repel. So electrons outside the nucleus, they want to be as far apart from other electrons, and so they compete to be as close as possible to the nucleus, but also they can't all be on the first energy level. That just wouldn't be it just wouldn't be energetically stable. And so what happens is that it takes more energy for an electron to be out here than it does to be closer to the nucleus. So if you're further away from the nucleus, it's more energy, which is also why if an electron absorbs energy, it's going to move further away. Okay, and then we already talked about the ground state and the excited state. So that's just from the past slides. I just want to have it in definitions here. And so when an electron absorbs energy, it jumps to a higher position, a position further away from the nucleus. That's called a quantum leap. It'll be in its excited state. It will not stay there for very long. And when it falls back down, it will emit energy. It will drop back to a lower position, so it'll be lower in potential energy, but it's going to emit energy in the form of light. So literally, when you see light, you are seeing electrons moving. And this happens, there are, trillions of electrons in any one atom. And when they're absorbing energy, they're all making these quantum leaps up and down, up and down. And your eyes just see it as a straight light, but just know that literally there are the electrons moving. That's what you're seeing. So here is something as part of the lab. It's a visual diagram here. And what it's trying to represent is, let me kind of scroll this down. So here you have, this is just a different depiction of this previous slide with these energy levels, 1, 2, 3, 4. Okay, so here you have N represents the energy levels. So you've got the 1, 2, 3. I'm going to scroll up. 5, 6, and then 7's just outside of the screen of this. Let me shrink it here so that we can see it all. My slide. So what this is saying, so this is actually going into more specifics. So what happens when you have an electron on the first energy level, and let's say it gets promoted to the second energy level and falls back down? It's going to emit UV light. Any electron that absorbs, that was its ground state is in the first energy level, and it gets bumped up to the second, third, fourth, fifth, sixth, or seventh, and then falls back down, is going to all be emitting the UV light. That's just the amount of energy that gets released when you promote an electron from the first energy level to any other one. Now, we see the colors of the rainbow when an electron that is normally its ground state is in the second energy level. And so literally when you see red light from a flame, that is electrons absorbing energy from the second energy to the third and then falling back down. That's when your eyes detect red light. When your eyes detect blue light, an electron goes from the second energy level up to the seventh and then falls back down. And when it does that, it emits blue light. And so as we talked about what lights have different amounts of energy, I hope that you can see that it takes a way more energy to promote an electron from the second to the seventh energy level, which is why a blue light has more energy than a red light, because it doesn't take as much energy, or not as much energy is absorbed into the system, and then when that energy gets released, because it only went from the second to the third energy level, that red light is lower in energy. And then you can see on here that infrared radiation is when an electron gets moved from the third energy level to the fourth, fifth, sixth, or seventh, and then falls back to the third. So depending on where an electron started and where it gets promoted to determines the type of electromagnetic radiation that occurs. And so the whole electromagnetic spectrum, from gamma rays to radio waves, okay, our eyes detect this little sliver, and those are very specific energy, amounts of energy that electrons absorb so that we can see the colors of the rainbow. And then other electron quantum leaps will produce light. Remember that light is anything on the spectrum, depending on how much energy it absorbed and how much it's releasing. So a little bit more about when you were heating stuff up, what are the electrons doing? Okay, so this is what people were studying. Okay, this is what Bohr was studying. So this is kind of going backwards a little bit, but okay, how did people figure this out? Well, back in the day, it was, a little over 100 years ago, people began noticing that different elements gave off different color lights when they're heated, and that's called their spectra. Okay, it's called the atomic emission spectra as well. It's just another word for what they call it. Now, back in the day, they didn't have all this fancy equipment, but what they did have was prisms. So they probably didn't have a Bunsen burner. They probably just had some kind of fire, and they heated the sample up, and they put it through a slit, and then some kind of prism. And a prism basically diffracts the light, and it allows you to see what colors are within that sample. So when you guys were seeing the flames, you might have seen a red color, or maybe you saw a green color. Macroscopically, that's what your eyes detected, but if you put it through a prism, that color might be actually made up of multiple different colors. Well, this was weird to scientists. Okay, not only was it weird that when you heated different things produced different colors, just like you saw in the flame test lab, but then when they put it through a prism, they saw kind of some unique banding patterns, and this is what Bohr kind of based his work off of. He thought this was weird, which it was weird, but he was a genius and explained what was actually happening. So what people found is that all material, when heated hot enough, will emit some kind of light, some type of electromagnetic radiation. And most material will emit light in the visible spectrum. And you can use a prism to emit light. You can also use a fancy spectroscope, which we will get to do. But what Bohr found and other scientists found is that every single element and compound has its own unique banding pattern. And it's like a fingerprint. It actually allows scientists to determine what elements are in certain samples because every element has its own unique banding. And the reason for this is what we've been talking about through this video, is that every different element or compound has a different number of electrons. And every single electron in a compound or an element makes different quantum leaps. And so they're moving away from and back from different ground state positions, and they're going to give off different color lights. And so that's going to create different patterns. This is what's known as the atomic emission spectra, the atomic line spectra. This is mentioned on a couple of your homeworks, and I just wanted you to be aware that the banding is called the atomic emission spectra, which I have on the next slide some examples. So this is what Bohr and other scientists noticed, is that, so they heated up hydrogen gas. They put it through a prism, and these are the banding patterns that I'm talking about. So these are all atomic emission spectra. And hopefully what you can see here is that hydrogen's spectra looks different than helium, a different element, which looks different than neon. And so, one, it's awesome, but I hope that you see that it allowed scientists to identify different elements and know that if they had an unknown sample, they could compare it to the banding patterns of pure samples that they had seen. And also, this was a time when they were figuring out tons of new elements, and if they thought it was something new, then it wouldn't have banding patterns for anything they have documented, but if it wasn't, then it would match up to something that they had. So sodium, mercury, what else do I have got? Oh, this would be like your unknown, and it lines up really nicely with mercury. So say you had some unknown solid and you didn't know what it was. This is literally what forensic scientists do. It's also what astrophysicists do when they're studying the stars in cosmology. They will look and basically diffract stars to see what their chemical composition is and get an idea for what elements are present in those planets. So this is a cool factor of, or cool result of science and how it's helped us kind of progress it. Now, Bohr's genius is that he looked at these spectra and kind of backward engineered this idea that it must be electrons in motion. And so him and Planck, Max Planck, and Einstein then took this work to develop his photoelectric effect. But they basically had this theory that electrons emit or absorb energy in these discrete units called quantum, or quanta, plural. And these gaps that exist from these atomic emission spectrum, these empty spaces in here, okay, these are like the discrete amounts of energy that the electrons can't go anywhere. So this is saying that the electrons in a hydrogen atom can only be promoted to certain positions outside the nucleus. They don't just fill in everywhere. Now, hydrogen's number 1 on your periodic table. And it has 1 proton, 1 electron. Iron is number 29 on your periodic table. No, 26. 26 on your periodic table. So it has 26 protons, 26 electrons. It has more electrons, so it has more banding. And if you even go back to the other slide with some of the other elements, helium's number 2 on your periodic table, neon's number 10. You can see, now sodium's number 11, it doesn't have a lot of banding, but it tends to be more banding as you go further down the periodic table. But like I said, every single element has its own unique banding pattern that is unique to it. And so this idea that energy is quantized, it's discrete, So what that means is that it can only exist in certain points. And I think a good analogy for that is that light, it's like walking up or increasing in altitude. It's the difference between walking up a ramp versus walking upstairs. So if you walk up a ramp, you can stop at rest at any altitude, anywhere on the ramp. Versus if you walk up some stairs, you can only stop at like step 1 or step 2. You can't be at a place in between it. And so those gaps that exist in the emission spectrum are basically, they're like different steps on a staircase. So electrons are like this. They only exist at certain points around the nucleus. And so that's why we see the banding. We don't see what's called a continuous spectrum. You don't see the full rainbow. A full rainbow is considered white light, and that's where you have a continuous spectrum. You do not have the banding pattern. So to try and wrap this up, hopefully, an electron can only absorb and release certain amounts of energy, which is called quanta. Every different type of light has its own unique wavelength, frequency, wavelength, and energy. Light and energy and matter interact, and that's how we experience the electromagnetic spectrum. That really cool intersection between light and energy and matter, how electrons and light interact. Super cool. And that electrons have certain energy just like light. So matter has energy and light has energy, and we can calculate that with numbers, and we can also conceptualize that, which is what this video is trying to get at. So I hope this video lecture is helpful, especially if you are absent, and as well as you can go back and review any of this or come with questions next class on anything covered in this video.